Good morning, everybody. I hope you had a decent enough Christmas. So today I want to talk about this kind of, we'll call it a scaling paradox, but people have been saying, scaling is giving out and LLMs are hitting a wall for a while now. But despite that, the objective measurements continue to improve. So when we look at actual capability, it continues to scale disproportionate to the rest of the scaling law returns. Now, this is not just data and compute and test time compute. It really it doesn't make any sense. That we're not really able to predict how much additional capability gets added despite the diminishing returns of traditional scaling laws. So let's unpack this and figure out kind of what's going on. Now, at the beginning, the narrative was simply scale is all you need. You look at GPT-2 to 3 to 4, each time it gets about 100 times bigger. Or I guess this is a 10x increase. This was about a 100x increase. So the whole idea was that proportional improvements in capability from scaling inputs on a fixed transformer architecture. So the curve was relatively consistent. More data, more compute, better performance. And so this has been kind of the name of the game for a while. Parameter count and compute budgets became the primary metrics of progress. That is kind of what we know and understand. Now, however, when we look at kind of the two things that people are saying, and there's the objective, both are objectively true, but they're mutually incompatible. So we need to figure out like how and why. So scaling is hitting a wall. Prominent voices argue the original paradigm is yielding diminishing returns. Gary Marcus in 2022 said deep learning is hitting a wall. Obviously, that didn't age very well. And then Ilya Sutskever even highlighted the need to overcome peak data, emphasizing we have but one internet. The technical claim, returns from simply adding parameters and data to vanilla transformers are diminishing. That is objectively true. Now, however, capability is still accelerating despite the diminishing returns over here. So objective real-world benchmarks show that what AI systems can do is improving faster than ever. Machine autonomy is improving at a logarithmic exponential rate, according to METR. New reasoning benchmarks are being saturated in months rather than years, namely ARC-AGI, just as one exemplar of that trend. So then the question is, how are both of these true, and what does it mean for the future of artificial intelligence? So first, here is kind of the curve of meter. So long-term trend, the length of tasks achieved by generalist agents can complete has been doubling approximately every 7 months for the past 6 years. However, recently it accelerated to just every 4 months. This came 3 years after Gary Marcus said, it's hitting a wall. So where was the wall? Where was the wall on machine autonomy, right? Where was the wall when Gondor called for aid? Sorry, wrong fandom. Anyways, you get the idea. I've talked about this, and people have talked about the meter. And so you're like, well, this is something else entirely, but it's like, is it really something different when we're looking at the actual capabilities of a model, which when you look at the behavior of it, the actual capability of the model, that's more important than whatever scale alone gives you, which is utility. So the utility is accelerating faster than, whatever underlying predictions happen from just scale alone. So utility is accelerating regardless of what scale is doing. Now, another example is benchmarks. So reasoning benchmarks are saturating at a stunning pace. The story of ARC-AGI Prize illustrates the disconnect between scaling debates and real-world problem-solving progress. Now, ARC-AGI is not a real-world problem, but the fact of the matter is it took 4 years to go from 0% to 5%, and then it took months to go from 5% to near saturation. So they had to release ARC-AGI 1, then ARC-AGI 2, and now they're already working on ARC-AGI 3. This was supposed to be a grand challenge. This was supposed to be a challenge that was going to take years or decades to saturate, but now they're already working on the third version, saying, oh, it's going to get harder and harder. And ARC-AGI 3 apparently is going to be interactive, meaning it's not just a static puzzle to solve. It's going to be something that reacts as you interact with it. I don't know the full details yet, but that's what the rumors show. So they keep having to move the goalposts on the benchmarks. And of course, this is just one benchmark. This is just one example. We've seen plenty of benchmarks where they're like, oh, well, we saturated that benchmark. We're going to need another one. And as those benchmarks continue to saturate, the models continue to get more and more useful and better at coding and better at agentic control and that sort of thing. So where's the wall? There's no actual wall in terms of actual performance or actual utility. That's the real big question. So the paradox resolves when we stop conflating one scaling vector with the entire capability frontier. People are really committing a category error here. The flattening of one curve, such as vanilla pre-training, is being mistaken for a slowdown in overall AI progress. The capability frontier is being pushed forward by multiple simultaneous research programs. So test time compute scaling, which is chain of thought, search, tool use, architectural innovation, such as mixture of experts and SSMs. I'm not really sure what the SSMs are. It just got stuffed into all of my research. Agent scaffolding and tool use, post-training improvements, better training recipes, such as RLHF, DPO, synthetic data, self-play, all of those things. So when they say scaling is dead and scaling is all you need, crowds are both missing the point. Progress is an empirical question, and the empirical trend is a function of all of these vectors combined. It's not just one thing, because, I mean, remember when they released GPT-4 and everyone's like, wow, what's the secret sauce? And Sam Altman literally said it's not one thing, it's like hundreds of little improvements. So it's not just that you have to throw more data at it and more compute at it. That was, kind of the top line. But there's hundreds, literally hundreds, if not thousands of other improvements that you can use to increase the utility and capability of models beyond just a single scaling vector. So even with all of this, however, this is kind of what the purpose of the video is. There's a very, very large gap between machines and brains, and that is sample efficiency. So the gap is not just a quantitative difference, it points to a qualitative algorithmic one. There is something that human brains are fundamentally doing differently. So human brains can generalize from a handful of examples, whereas machine learning requires millions or billions of examples to learn. So one way to think about this is you can train a language model on literally hundreds of trillions of tokens, whereas human brains train on maybe 100 million across your entire lifetime, or at least until you are able to generalize. So our brains are doing something very fundamentally different. And this is not a new piece of information, but I want to address one pushback that people have, which is that evolution endowed us with, we inherited billions of years of evolution, which comes with a lot of baked-in knowledge. That is true insofar as we have certain instincts, like for locomotion and speech and that sort of thing, but we don't have any evolutionary instinct for things like calculus or economics or even reading and writing. Those are skills that we have to graft on that our brains really aren't even wired for. So we can learn to read, write, do economics, do math, do computer science and programming. None of those we came with. Evolution doesn't have any template for those things. Yet we can still master them with relatively few data points. So our sample efficiency is just orders and orders of magnitude much better than silicon still is today. So the data wall really is a compression wall, because if a system that could actually extract and generalize from the data already available on the internet would be superhuman. The bottleneck isn't the amount of data, it's our ability to compress its essential structure and extrapolate from that. Think of it this way. If you had a human that was able to learn everything that is being put into all of the data sets for these AIs, that human would be far, far smarter than all of these AIs. But the AIs are still compressing it, and it's a lossy compression, and it's not a particularly good compression. So something else is happening. And now this is not to say that intelligence is just compression. It's an artifact of compression, abstraction, generalization, distillation. There's many, many other information processes happening, but the shorthand is artificial intelligence is compression. So we need a better compression algorithm that allows us to generalize all the information that we already have even better. So the next paradigm is rooted in a fundamental principle. Compression forces understanding. The idea that compression and intelligence are deeply linked is gaining significant traction. To efficiently compress data, a system must learn a model of the process that generated the data. So you start with raw data, you come up with an optimal compression algorithm, and then you have a learned world model. Ilya Sutskever says, it looks like we are just learning statistical correlations in text, but to compress them really well, what the neural networks learns is some representation of the process that produced the text. To understand those statistics, you need to understand what it is about the world that created that set of statistics. So basically, this is more of a like information theory and entropy version of reality, which is, it at the surface level, what he's saying is that right now, language models and AI are learning patterns, which, learning patterns and pattern recognition and pattern generation is the beginning of intelligence. This is true, but you need more layers of what you might say ascending up the abstraction hierarchy. So while they have some levels of abstraction, which we've been able to see in tests, like theory of mind and metaphor, AIs are able to engage in theory of mind and metaphor, whereas earlier versions were not as good at that, and that is an example of layers of abstraction. So that's not to say that like, oh, we need to RLHF more abstraction into it. There's probably something else going on, but this is where we're converging. So frontier research is already validating the compression first approach. The case study is DeepSeek. So they used optical compression, DeepSeek OCR, inverts token hierarchy. They used visual representations as a superior medium for text, achieving 7 to 20x token reduction. In other words, by making the AI just read text the way that we do, it used fewer tokens, which is a really interesting, very dramatically interesting result. Architecture efficiency. So they used MLA, multi-head latent attention compresses key value vectors, there we go, sorry, to drastically reduce memory demands for the KV cache in long contexts. And then compute efficiency, completed pre-chaining on 14 trillion tokens with only 2.8 million H800 GPU hours at about a cost of about $5 million, dramatically less than competitors. Are pixels better inputs to LLMs and text? Text tokens might be inherently wasteful, Andre Karpathy. So we're finding different ways of increasing the efficiency. So when we look at like, what does this really mean? Because the research question that drove my research into that became this video was, all right, what are the constraints and where is it actually going? So there are 3 fundamental forcing functions that make sample efficiency the inevitable next frontier. Number 1 is compute constraint. Access to frontier scale compute is limited as demonstrated by China and labs like DeepSeek. Necessity breeds efficiency. When you can't buy more GPUs, you find better algorithms. Now, we're all going to be compute constrained. And just by dint of the fact that the demand for AI is going up, it's doubling every 6 months. And yes, make more GPUs, great. But then as we want the AI to be smarter, not just more of the same, we're compute constrained. Next is power constraint. Economic and environmental limits on energy consumption make ever larger models unsustainable. The future requires more intelligence per watt, which is a direct function of algorithmic efficiency. Smaller models take less energy to run. It's that simple. More efficient models take less energy to run. And then furthermore, when you look at physics as a first principles constraint, entropy, the human brain dissipates about 20 watts of energy and does way more than all of the AIs do already. So, it's like, what's the actual constraint there? Or what's the actual ceiling or floor, depending on how you want to look at it. And then, of course, data constraint, the compression wall. The bottleneck isn't a lack of data, but inefficient learning, rather. The internet contains more knowledge than any human needs. The challenge is to extract its structure efficiently, not just hoard more private data. So this reframes our definition of intelligence itself. The discourse has been optimizing for the wrong metrics. We should focus on the primitive, not the emergent capabilities. So the levels of abstraction problem. So discourse, so this is the level that we've been talking, N+1, and the actual mechanism. So people were worried about instrumental convergence, but the actual mechanism was next token prediction. Then people will talk about AGI and they say it needs continuous learning. But what we're really talking about is rapid generalization. And then people like Francois Chalet talk about skill acquisition efficiency. But really what we're talking about is sample efficiency. So what we need to do is really look at one level of abstraction below what people are actually talking about or aiming for with artificial intelligence. So the key insight, continuous learning is a consequence, not a cause. A system with sample-efficient rapid generalization will learn continuously by default. Focusing on the primitives is more predictive and productive. So basically what I mean is that once we have algorithm models that are highly sample efficient and rapidly generalize, you'll have a pre-trained cognitive engine that can pick up any skill very quickly in context. Now, whether or not that means online learning, like continuously changing the model weights, I don't think that that's necessary. For instance, humans can generalize to any new task as long as you've got enough generalized skills and knowledge, generally pretty well. Now, we do get better at things over time due to ongoing neuroplasticity. So maybe, it would be ideal to see some level of neuroplasticity in the future. But I think honestly, the better thing is just to have a generalized engine that is already generalizable to any task it could possibly see. The real goal, the challenge is not scaling parameters, but scaling abstraction depth, causal model fidelity, and learning efficiency itself. So the governing paradigm of AI progress has really shifted. In 2017, attention was all you needed. That was the architectural primitive. Next, from 2020 to today, scale is all you need. From here on out, it's sample efficiency is all you need. Now, obviously, we're going to probably come up with another paradigm, but when you look at the numbers, when you look at the math, when you look at the first principles, it is very clear to me that sample efficiency is going to be the next big thing for at least 2026, 2027, maybe beyond. Who knows? This might be the next paradigm for the next 5 years, might be 10 years. It might be forever. I doubt it. I'm not going to hold my breath, but it's certainly the next big frontier right now. So I hope this helped you understand kind of where scaling is and added some to the conversation around what AGI actually might look like. And I'm not going to say that sample efficiency alone is going to solve AGI, but it is, to me, very clearly the next step towards, whatever the next paradigm shift is going to be in artificial intelligence. So thanks for watching, and I'll check you all later.